and welcome back everyone. This video will cover topic about modular binary exponentiation, and it is the continuation of binary exponentiation method discussed in the last video. In case anyone hasn't watched the last video, kindly have a watch before proceeding towards this topic. Here, as either A or B can be greater and it may not fit within the range of either int. So to carry or to make that value fit in the some data type, modulus operation has to be applied, and generally it is represented as a power b whole mod of m, which is saying as a which is multiplied b times and then taking the mod. And by the modulus property on multiplication, this can be written like a mod of m times a mod of m and so on, repeated b times, as the multiplication may lead to overflow in some data type. Hence, to prevent that, again mod has to be applied. This is how it will be worked out. But using naive Bayes or naive approach, this may be very tedious or it may be very time consuming. Hence, recursive or iterative approach would be preferred, and generally binary exponentiation from left to right will be preferred, as it was said that it is faster than when compared to right to left. Why? Because here only smaller value would be computed first, and in the binary exponentiation from right to left, multiplication gets more tedious as well as the value keeps on increasing. Hence, it's slightly faster, but both are of or big O of log of n time complexity. And this approach will be applied on the modulus binary exponentiation. Before diving into the pseudocode of this, let us have a look at example to understand the idea of how modulus operation would be applied. Consider an example of base, which is 14, raised to 31, mod of 11. And as it was discussed in the video, where this can be written in the binary form, which is 16 plus 15. So this all will be ones, and mod 11. And in the binary exponentiation method from left to right, how squaring and add operation was taking place, same thing can be applied here. And to understand the idea much better, the idea is simple, where this base, let's say this is A. So first, whenever 1 is encountered, it will square, and whenever 0 is encountered, it will again be squared. So this will be squared and so on. Why? Because considered 14 raised to 0, which will be 1. So it will be starting from 1. Then it will be 14 raised to 1. And since it is a binary number and 2 in binary can be written as 1, 0, which is nothing but a raised to 1 times a raised to 1, which is a raised to 2. And in binary it can be represented as 1, 0, right? So it is 1 here, 14 raised to 2. And for 3, what we need to do is a raised to 2 times a. So in binary it can be represented as a11. Hence, whenever an odd number is encountered, 1 is added. That is, base is added to the number. But whenever an even number is encountered, let's say a power 4 has to be encountered, so which is nothing but a square times a square, and a square is written as a of 1, 0 in binary times a of 1, 0, which is nothing but a of 1, 0, 0. So in case the next value would have been 0, then square would have taken place, like here. But in case the next digit is 1 in the binary representation, then 1 more times a has to be added. Using this, so this idea is known as square and multiply method. First we are squaring, and in case multiply has to be performed, it is being performed on the even and odd case. So square will be performed on the even case and square and multiply will be performed on the odd case. And as from the recursive example also, you must have clearly seen it. Now using this idea, let us work it out. So first will be 1 followed by 14 raised to 1, since 1 is being encountered here, and again, so this will become 14 raised to 1 mod 11, and since 1 is encountered in the next iteration as well, which is 14 raised to 1, 1, which is equivalent of saying 14 raised to 1, 0 times 14 raised to 1. So in binary addition takes place, this becomes 14 raised to 1, 1. So this is generally 14 cube mod 11. And again 1 is encountered, it will become 14 cube. So this has to be squared, and then 14 has to be multiplied. So this will become 14 raised to 7 mod 11. Why mod? Because individual mod has taken place by the modulus property. And then 14 raised to 7 square, because again 1 is being encountered, then adding 1, so this becomes 14 raised to 15 mod of 11, and then 14 raised to 15 square times 14 will give us 14 raised to 31 whole mod of 11. So from here one can check how many computation will take place. So here 14, this is one computation, here this will be another computation. So this becomes a log n computation, and let us try the value of each of the steps. 14 mod of 11 is 3. 14 cube mod of 11 is basically saying 14 times 14 square. So 14 square can be written as 14 mod 11, which is 3. 3 cube, basically 3 cube mod 11, which is 5. And here it will be 3 power 7 mod 11, which is 9. And 14 power 15, which is equivalent of saying 3 power 15 mod of 11, which is 1. And 14 power 31 mod 11 is equivalent of saying 14 raised to 15, which is 1 times 14. So this answer should be 3. And here is an interesting observation that one can make. Let's say 14 raised to 0 mod 11 will give us the answer 1. 14 raised to 1 mod 11 give us 3. 14 square mod of 11 gives us 9. 14 cube mod 11 gives us 5. 14 power 4 mod 11 gives us this is 3 power 81, so this will become 4. And 14 power 5 mod of 11 will give us 1. And from here again the same pattern will repeat. For it can be written in a way that a raised to some binary number of p minus 1, p minus 2, and so on till b of 0, where b of ti is the bits. So for squaring, how many bits would be required? So 1 0, let's say even number, 2 bits would be required. So that means for t minus 1 bits would be required. And for multiplication, 1 bit would be required. And 1 bit for each of the total t minus 1 bit would be required. So this is t minus 1 bits, here t minus 1 bits. Total for square and multiply operation, two times t minus 1 bits would be required, and this would be the worst case scenario. And what would be the best case scenario? Only squaring will take place. So, and that will require 1 bit. So squaring requires t minus 1 bit, and it is the best case scenario where the number is even. So using this idea and applying the idea here, how many options have taken place? So, rewriting it again, 14 raised to 1 1 1 1 1. there are 5 bits and total number of operations that would have taken place. For first bit, only square operation has taken place, which is 2 one operation. For second bit onwards till the end, 2 operations has been taken place, 2 into 4. Total of 9 multiplication will take place in this, or 9 times operation will be carried. Here 1 time for the first bit and 8 times for the remaining 4 bits. 9 operations will be carried, which can be justified from the formula, where only first case squaring takes place. So 1 operation will be taken place, followed by 2 times t minus 1, which here t is 4, 5 minus 1, 4, 8 bits will be. So these are the operations required. While 9 multiplication in general will take place, followed by some modulus operation. But using the naive approach, here 31 will take 30 multiplication and followed by 30 times modulus, 31 times modulus operation. While this will take 9 multiplication operation plus 5 times modulus of 6 times modulus operation. So in general 15 operations will be required to compute the value of 14 raised to 31. Only 15 operations will be sufficient. So you can see how drastically the number of operations have reduced from